Welcome back to the Institute of Rock Crawling. Today we're going to be talking about traction. Traction is what allows you to climb, traverse, an incline or obstacle. Transverse and longitudinal stability is what allows you to do that without rolling over. These are important concepts to understand, but today we're going to just talk about traction. Traction consists of both frictional and gear loading. Let's first talk about frictional traction. We will use the following references. The at sign is the inclination angle of the surface you are traveling in degrees. The weight is the gross weight of the vehicle in pounds. And CF is the coefficient of friction. So let's look at traction on a level surface. Traction equals the weight times the coefficient of friction, where weight is the weight on axle and CF is the coefficient of friction. In rock crawling, the coefficient of friction can vary from second to second and tire to tire. A coefficient of friction is a composite theoretical factor with many components. From practical experience, we know that a high pressure tire will produce less traction than at low pressure on off-road surfaces. The off-road surfaces cannot resist the high shear loads that a high-pressure tire generates. That is why we air down. Airing down decreases the PSI loading while also increases the contact surface area. These two factors reduce the shear load friction between the tire and the road surface to a level that the road surface can provide, thus increasing traction. Traction is a function of PSI, surface area, and the shearing resistance between the road surface and the tire. Weight is the PSI times the surface area. And traction equals the weight times CF, or the PSI times the surface area times the coefficient of friction. And the coefficient of friction is a function of PSI and surface friction. If the PSI is greater than the surface friction, then slippage occurs. As a general rule, the lower the PSI, the greater the coefficient of friction, and therefore traction. Traction is a resistive load between the road surface and your tire. We use that resistance to propel the car. So how much torque is required to generate traction? Let's take a look at our tire. You can see R is the radius of the tire, and the torque required equals the traction times the radius of the tire, and the units are foot-pounds. Our engine has to provide this torque, and the transmission and drivetrain has to transfer it to the tire. So let's look at the issue of tire size. The larger the diameter, the easier it is to drive over obstacles. This is great for rock crawling. The downside to that is that a larger tire requires more torque to deliver the same traction than as a smaller one. Let's use a Razor XP1000 as an example. Factory configuration comes with 29-inch tires. The entire suspension and drivetrain has been designed around this tire size. If we put a 35-inch tire on this vehicle, which I did, what does it do to the torque requirements in relationship to the factory loads? Well, it's easy to calculate. 35 inches divided by 29 inches equals 1.2. This means that in order for the 35-inch tire to develop the same amount of traction as the factory tire, it requires 20% more torque. Let that settle in. The entire drivetrain was not designed to carry this extra load. If you put a 28% gear reduction in your transmission, you will still be overloading your entire drivetrain. The weakest link is still probably the axle CV joint when articulated. The only solution to running oversized tires is portals. If you use a 30% portal, you will have reduced the overall torque loads in your drivetrain by 10% less than factory with the 35-inch tires. However, this comes with a price. You will significantly increase your steering loads due to the 4+ inches offset due to the size of the portal housing. Factory configuration for the front tires is 4x6 rims and a 5-1 offset on the front tires. The center of the tire is outside the alignment of the two steering pinions by 1.75 inches. The steering arm is 3.75 inches. This means as you experience rearward impulse loads to your factory front tires, the resultant load put into your rack and pinion mounts is reduced by 0.47. The best solution to have the tire center line in line. The best solution is to have the tire center line in line with the steering pivots, which would eliminate all steering loads. Now let's look at using a 5.2 offset rim with a 4-inch wide GDP portal. The offset is 6.5 inches from the tire center line to the steering pivot line. This amplifies the tire shock loads by a factor of 1.625. Use of a 6.1 offset rim will amplify the load by a factor of only 1.46, a slight improvement. Using a larger offset can further reduce the momentum arm. Let's look at a 15x7 rim with a 5.2 offset. As you can see, a 6.1 offset would not work with a 5.7 rim. You could use a 6.1 offset with a 17-inch rim. That would reduce the load factor to 1.2. Every bit helps. So let's look at the traction required to climb an incline. So the sine of the incline angle times the weight, it's the force pulling you down the hill. That's the y factor. And the cosine of the inclination angle times the weight is the contact force between the tire and the surface, and that's labeled as x. The weight component pulling you down the hill must be less than or equal to the traction force. So the cosine of the inclination angle times the weight times the coefficient of friction has to be greater than or equal to the sine of the inclination angle times the weight. And this reduces to the coefficient of friction must be greater than or equal to the tangent of the inclination angle. You can see that the coefficient of friction required is independent of weight. One of the factors affecting coefficient of friction is a tire's contact surface area. This can be improved by airing down or by using big fat tires. Airing down also momentarily reduces the working radius of the tire and reduces torque requirements. Let's look at a chart of inclination versus coefficient of friction required. Of note is that at an angle of 45, the coefficient of friction is 1. So the coefficient of friction cannot exceed 1. So all the table values which exceed 1.0 require a gear loading on the tire treads to continue the climb. In practice, any inclines greater than 30 degrees probably require some degree of supplemental tire gear loading. On the trail, the coefficient of friction and the inclination angle for each tire dynamically changes every moment. You can always tell when the aggregate coefficient of friction for your vehicle is less than the tangent of the inclination angle, because that is when all your wheels are spinning. Can you climb inclines greater than your traction limits? No. However, if the incline is of limited duration, i.e. height, then you can exchange kinetic energy, which is 1/2 mv squared, for potential energy, which is weight times the height. Here is a chart that will tell you what speeds will result in additional height. It does not account for friction loss, which is really minimal. Okay. The conversion between kinetic to potential energy seems rather meager at rock crawling speeds, but every bit helps. However, a bump is actually doing much more than trading energy states. The bump causes the tire to momentarily compress and increases the tire to surface area, as well as increases the tire pressure. This increases the coefficient of friction and therefore the traction. Traction from gear type loading. If your tire has an aggressive tread and the road surface has sharp edges that the tire tread can engage, then the traction that that tire can provide is significantly higher than from just frictional loads. The load is only limited by the tangential shear load limit of the tire tread, which can be quite high. It is clear that the predominant trail traction loads result from gear type loading. The more tread engagement, the more traction. Use of tire chains act as aggressive treads and can be used anytime. Just watch out for the sparks and resultant wildfires. The engine must be able to provide enough horsepower at relatively low RPMs when rock crawling. 1 horsepower is 32,000 foot-pounds per minute, and 1 mile per hour is 88 feet per minute, or 1.47 feet per second. Okay, so the horsepower required to climb is weight times the sine of the inclination angle times the feet per minute. Let's look at a table of horsepower required for a given incline for a weight of 2,000 pounds at 1 miles per hour. You can double these numbers for 2 miles per hour. As you can see, it does not take a very large engine to be able to crawl. Side-by-sides use CVT clutches. It takes a certain amount of RPM before the clutch will engage the drive belt. Often this engagement RPM is not enough to move the vehicle. More throttle is required to achieve the breakaway torque to climb. The belt slips until this minimum RPM torque is achieved. It is very easy to overshoot this throttle value, which results in a lurch and subsequent backing off on the throttle. This often results in a series of lurches. This is hard on your clutch and drive belt. If this is happening, it is a symptom of incorrect gearing. You need to lower your drivetrain gear ratio. I have 30% portals with an internal 28% transmission gear reduction on my Razor. This results in a reduction ratio 38% lower than factory. This has helped greatly, but a further reduction would be better. If Super ATV releases 60% 4-inch portals, I will buy them to get the extra 30% reduction. There is another condition that will also cause lurching. It is difficult to maintain a constant throttle setting while my throttle leg is bouncing around. This picture depicts a simple foot restraint system that I use. The bungee cord ensures that my foot will never be trapped if I had to exit the cab quickly, but still provides enough force to keep my foot on the pedal while being bounced around. We will cover longitudinal and lateral stability in the next video. Thanks for watching. Smash the like button.